Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face Trending List, published on January 20th, 2026, just 3 days ago. It introduces a new family of grounded vision language models that more than doubles the grounded OCR performance of the QN 2.5 backbone, jumping from a score of 0.40 to 0.82 on over 10,000 held-out pages. The paper is titled, GutenOCR, a grounded vision language front-end for documents. And as we'll see later, the way it unifies reading, detection, and grounding into a single prompt-based interface is really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. You can grab the 3 billion and 7 billion parameter models on Hugging Face today. They feature examples for full-page reading and grounding text using simple bounding box prompts. Figure 1 provides a detailed capability profile using a radar chart to compare the new models against their backbones and other baselines. The GutenOCR models, represented by the red and purple dashed lines, form a wide outer shell across the top and left sections of the graph. This visualizes their dominance on in-domain detection and local reading tasks, where they score nearly 1.0. In contrast, the blue solid line for the original QN 2.5 backbone sits much closer to the center, showing it lacks these fine-grained grounding abilities. However, the bottom right axis reveals a trade-off, as the new models perform slightly worse on color-guided tasks compared to the specialized parsers. Figure 2 illustrates the unified interface that makes this versatility possible. At the center, the single GutenOCR model acts as a hub for 4 distinct tasks. On the top left, the detection mode takes an image and outputs bounding boxes for all text. Opposite that, on the top right, the reading mode generates full transcripts, which can be plain text or structured formats that preserve layout. Moving to the bottom left, we see conditional detection, where the model accepts a specific query like a name and returns its location. Finally, the bottom right shows localized reading, which does the reverse. You provide a box and it transcribes exactly what is inside. Table 1 lays out the specific prompt templates that control these behaviors. The reading section at the top highlights the model's flexibility. Beyond standard transcription, you can request a text2D format to preserve layout, or ask for lines to get structured JSON objects with coordinates. Below that, the detection prompts allow you to target specific document elements, like paragraphs or even math regions, returning only their bounding boxes. The final rows cover the interactive tasks, showing how the input expands to include text queries for finding content or boxes for targeted reading. Table 3 outlines the training recipe, which uses a length-based curriculum. This means training starts with short, simple inputs before tackling longer ones. Stage 1 begins with sequences under 2,000 tokens from mixed sources. By Stage 2, synthetic data is dropped to focus on real business documents up to 8,000 tokens. Finally, Stages 3A and 3B specialize in scientific articles from PubMed, extending the context window to 16,000 tokens. So Table 6 quantifies the impact of that curriculum on in-domain performance. The columns are split between reading errors, which we want low, and detection scores, which we want high. Looking at the 7 billion parameter group in the middle, the base model starts with a composite score of roughly 0.40. The GutenOCR fine-tune doubles this to 0.82, mirroring the gains seen in the smaller 3 billion parameter models above. Crucially, the detection scores leap from around 11% to nearly 79%, showing that the model is not just reading text, but accurately locating it. Table 7 shifts the focus to the Fox benchmark, which isolates specific skills like reading a defined region or a single line. The results in the region and line columns demonstrate the model's new grounding capabilities. For example, the 3 billion parameter model slashes region error from 0.26 down to 0.053. However, the color column on the far right exposes a significant regression. The error rate jumps to nearly 1.0, confirming that the model lost its sensitivity to color cues during the fine-tuning process. Wrapping up, the big takeaway is that GutenOCR successfully bridges the gap between vision language models and precise coordinate-based document understanding. By unifying reading and detection into one promptable interface, it offers a reliable front end for automated systems. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.